Okay, off we go, and of course I wasn't on the right setting there. There we go. Okay, so last time we were talking about Stokes' theorem and Gauss's theorem. I gave you all the sort of the quick intro. This is going to be kind of a three-dimensional version of Chapter 6, in a way, right? These theorems, Gauss's theorem and Stokes' theorem, in their ways, are kind of three-dimensional versions of Green's theorem and the other version of Green's theorem, sometimes called the 2D divergence theorem. So the big differences are not really in the underlying structures of the theorems. The underlying structures of the theorems are pretty much the same, right? And that's why I like to focus on that underlying structure, so you can see how whatever intuition you have for Green's theorem or the 2D divergence theorem, that intuition transfers over very nicely to these other theorems. So in particular, we have to be very clear and precise about what we mean by boundaries, in particular how boundaries are oriented, right? And in particular, here's what it is. The orientation is away from the solid, right? And we talked last time about how what that means is sometimes, such as in the case of this point right here, it means outward. But not always, right? You got to be careful about this. You don't want to subtly misunderstand an important rule. Away from the solid sometimes means inward, such as this point right here. Right? So heads up about that. Flashbacks to when we were talking about two-dimensional boundary curves and their orientations and how they could be kind of analogously misunderstood. Strong analogies. Okay. All right. The idea of accumulation. Again, we saw something like this when we were doing Green's theorem, developing Green's theorem. And in particular, what we have here is that boundary flux is our accumulating quantity. Specifically, boundary flux accumulates over solids. I'm going to add that clarification. So in other words, if you have an entire solid, and you talk about its boundary flux, and then if you chop that into pieces, and you look at the boundary flux of the one side and the boundary flux of the other side, the whole is the sum of the parts. This is what we mean by an accumulating quantity. Specifically, it is the solid, though, that I'm thinking of cutting and viewing the whole of as being the sum of the parts of. Okay. All right. So when you make this cut, the reason that this works is because when you make this cut and you look at this shared face that is created when you cut your whole into parts, right? Well, as part of the boundary of the left side, as part of the boundary of R1, the orientation is that way, again, away from the solid. Right? On the other hand, as part of the boundary of the right side, as part of the boundary of R2, away from the solid is that way. Right? That way. So, altogether then, when we write the boundary flux of R1 and the boundary flux of R2, this green face is going to show up twice. Partly as part of the boundary of R1 and partly as part of the boundary of R2. Shows up twice, but with opposite orientations, and therefore they cancel. Now again, flashback to Green's theorem. It's not exactly the same. This is three-dimensional instead of two. This is flux instead of circulation. But it's still, we look at the new edges, face in this case, but edge back in Green's. We look at the new stuff, and we notice that there's opposite orientations, and we get the cancellation. So shockingly similar. A real eyebrow raiser. And the patterns continue. Now this next part, this is, again, just a matter of point of view. I'm not really going to prove anything here. This isn't a new equation or anything. This is just kind of point of view stuff. But I claim that whenever you have an accumulated quantity, you can view it as being stuff. Even if it doesn't feel like it, even if, for example, of course, if you're talking about a solid like this, we kind of feel like boundary flux happens on the boundary. It's right there in the name, boundary flux. We compute it on the boundary, right? But just because we compute it there doesn't mean we have to view it there. boundary flux is a quantity that we associate to the solid. The solid is what we're chopping up into pieces. Right? The solid is the thing whose whole and the thing whose parts, blah, 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 right? So think of it as, because it's associated to the solid, think of it as being distributed over the solid. And I know that sounds weird, and so I'm going to remind you. We talked about this same idea concerning change. Right? The point of view I want to push on the fundamental theorem of calculus is that it's an observation of the accumulation of change. And this weird new take on derivatives as being a density of sorts, right? And so again, let's just talk about, where are the quantities computed versus where do they really happen? Where is it really, right? So change, you're right, we compute change by looking at the boundary, by looking at the endpoints, f of b minus f of a. That's how you compute how much something's changed. But it happened in the interior. Couldn't be more natural, right? That you can see the change happening. It's happening here, right? So that same point of view is what I want you to sort of encourage in yourself when you're thinking about boundary flux. Yeah, sure, you compute it on the boundary, but try to view it as if it's actually happening in the interior, and then you can talk about, okay, well, how much of it is in that little box? And how much of it is in, this little box next to it, and then how much of it is in this little box next to that, etc. Right? And as such, thinking of it as a stuff distributed through the interior, you can view it as having location, and that's what we need to talk about density. Right? So, and again, this was the natural next step when we were doing Green's theorem. We talked about circulation as being an accumulating quantity distributed over the interior, which again is a weird, kind of point of view to digest. But then we talked about, well, what is the circulation per unit area? And here, following the analogy, we're going to talk about flux per unit volume. Like flux is the stuff, that's the accumulating quantity. Volume is what it's distributed over. Stuff per unit size is density. Just like when you're talking about mass per unit volume, that's a density because it's stuff per unit size. Totally analogous. All right, now here again is where I'm going to sweep some stuff under the rug. We just don't have enough time to go into all the nitty-gritty details, and I think for given y'all are mostly engineers, right? I think what the most important thing is to see these big pictures and to see these connections and the actual details of how we compute what this integrand is. Yeah, it's important, but it's not important in the sense of something that you're going to need 10 years from now when you're thinking back to multivariable calculus class and using that in your engineering context, and how are you going to be making use of it then? Will not be this calculation. It'll be all this other stuff that we were talking about: density, accumulation, boundaries, orientations. That's what you're going to need. So I'm just going to cut straight to the punchline. Flux per unit volume, naturally called flux density, is computed with this formula. That's just what it is. Given a vector field F, coordinates PQR, there's your formula. Now, just a reminder. Whoopsie, I was on the wrong thing. Oh, where am I? Here we go. Okay, reminder, this formula we have seen before. This is what we saw back in Chapter 3 as being called divergence. Right? It was a formula we kind of threw out there for no apparent reason. I made some baseless assertions about what it was and what it looked like, and just ask you to trust me, which again gives me the willies every time I have to do that. That's not what mathematicians like to do, right? But now we have a context for understanding where this formula came from, and I'll come back to that in a second. Anyway, the term is divergence. A common abbreviation is to call it div. I think it's pretty natural, pretty believable, right? Also, as discussed back in Chapter 3, we sometimes write it as del dot. Very natural, very convenient in a lot of ways. We're going to be using that a lot. But again, make sure to remember what these notations represent and why we care about this formula. The whole reason that we're interested in any of this stuff is because it is flux density. Because it tells us, given a vector field where we've computed some sort of a total flux, how much of that flux per unit volume, how much of that flux is happening per unit volume in a given general vicinity. Just like the reason you care about derivatives in the context of the fundamental theorem of calculus is because it tells you how much the function is kind of changing there. How much change, how much of this overall change that you're computing on the entire thing, how much of that change happens per unit size, again in this case length. So very natural. The geometric interpretation you have for derivative, right? There's this totally analogous geometric interpretation for divergence, quantity per unit size. Let me give myself a chance to take a couple of inhales here because I've been talking a lot for the last 12 minutes. So who has a question for me before we wrap this up and get a theorem and do an example? Everybody on board with what we're doing? All right. Okay. So, quick example, just to underscore this idea of again, how to interpret divergence and what you should think of it as. As I just described, what divergence indicates is how much flux per unit volume is happening at some point in the interior. So with that in mind, let's think about this example. Whoopsie, I keep it. Okay, here we go. So with that in mind, let's think about this example. We have a vector field. This vector field makes a flux through some boundary. We don't even need to specify particularly what the solid is or how much flux it is. There's a certain solid, there's a certain amount of flux that's happening on that, or that we detect on that boundary. And so when you've detected a bunch of flux, you can talk about at different points how much, in some sense, how much of that flux is coming from there and how much is coming from there. And which one is more coming from. Okay? And again, that's what divergence does. Divergence tells us how much of the flux, per unit volume, of course, is happening at these given points. So to answer this question, I'm going to compute the divergence. I'm going to plug in my 2 points. I'm going to see which one's the biggest. Right? More is happening where you have greater divergence. And so this point B, not A, B, greater flux density, and so more of the flux is coming from that general vicinity. Just like when we were looking at the fundamental theorem of calculus, again, wrong button. The easiest kind of analog to visualize. You look at a function like this, and you ask, is more change happening at 1 or at 2? Well, you look at the change density. The change density tells you which one has more change per unit length as opposed to which one has less change per unit length. So derivative is playing the density role here. Divergence is playing the density role here. What do you think? Is that satisfying? Okay. Cool. Let's move it along. We are ready to put it all together. We just have to put the puzzle pieces together. We already have the theorem in some sense. The theorem comes from, again, sort of 3 ideas. First is to think of flux which, to be fair, is computed with a formula. Let's think of it as a quantity. Let's think of it as a thing, not a formula. Not much of an observation there. The first big observation is that it's an accumulating quantity. Deep fact, not obvious. Not everything you can give a name to has this feature. That's an important ultimately, this is what makes it all come together. It's the fact that flux is an accumulating quantity. The fact that we can declare the whole to be the sum of the parts. That's the big nugget underneath all of it. And then lastly, that little bits of flux are computed by way of a density. And that density is divergence. So on each little piece, stuff is stuff per unit volume times volume. The stuff per unit volume is our density. Okay, and now, nice punchline. We have ourselves a new theorem. I'll do this in a better color. Our theorem allows us to compute boundary fluxes with triple integrals over the interior. Right? And this is Gauss's divergence theorem. Okay. Everybody all right with that? I assume and hope that y'all are all noticing the deliberate, for the purposes of emphasizing the power of these analogies, I'm writing the development of the theorem. I'm following the outline that's intended as much as possible to be a shameless ripoff of what we did with Green's theorem. So, there you go. Okay. All right, so let's use this. Question that we're going to address here is concerning the computation of a flux. It says it right there. Divergence theorem allows us to compute a flux. That's nice. Big picture, what we're probably going to do, we figure, is try to use this theorem to rewrite that flux as a triple integral. Just, see where we're going. Do notice that we have to be careful, make sure the conditions are all satisfied, and a very important condition of this theorem, if you're going to use this theorem, note very importantly, and it says so right here, it has to be a boundary flux. That's, again, the whole reason that this theorem works is that we have an accumulating quantity. We only get the accumulating quantity because we restricted our attention to boundaries. Right? Otherwise, there is no argument. Right? Also, very importantly, if you're not persuaded by that, if you're going to use this theorem, if you're going to turn this into that, notice you need a solid R. In particular, you need the thing that your surface is the boundary of. So if your surface is not a boundary of something, then there is no something over which to even talk about a triple integral. So not only is the theorem not true, there is no triple integral to talk about, much less something that's actually equal to your flux, right? So really important condition, very, very important. Make extra sure. And I make a big deal out of this because I've seen this on exam papers so many times, and it makes me sad every single time that I see students trying to apply Gauss's divergence theorem when their domain is not a boundary, and it just doesn't work. It's all nonsense. Yes.
So with boundary there, you mean a closed surface?
Yeah, it's closed surface, and that's right. And it has to. You need to be able to identify what is the solid whose boundary it is. Right? Yeah. So it is also a closed surface, but just to be more direct and just to hit the nail on the head, it needs to be a boundary. Yeah. Is that satisfying?
Yep.
Okay. All right. Okay. So we need to look at our details here. We've been asked to compute over this surface called S. S is described right here. It's the inward-oriented unit sphere. Let's ask, is that a boundary? And I'm sorry, it is not. And I know that this is, finicky, uptight, persnickety, etc., right? But we have it right here. The word boundary now means oriented away from the solid. And if you look at our you look at our surface and what it may or may not be the boundary of, our surface here, our surface is oriented inward, which is not away from the solid. So S, as described here, is not a boundary. And we cannot apply Gauss's divergence theorem. Yep. Everybody good with that? Again, analogies, flash back to the first example we did with Green's theorem. Right? I've deliberately rigged it up to be same problem. And we have the same workaround, conveniently. Even though S itself is not a boundary, if I look at the exact same surface now, just orient it the opposite way, right? Orient the sphere the other way, as indicated by that superscript minus sign. That is a boundary, right? And so, having made that observation, we can say, well, look, I get a minus sign when I orient the opposite direction. And when I've oriented the opposite direction, that truly is a boundary. Don't forget that minus sign, right? That carries along, right? And because it is a boundary, that then, this integral is the one that you can apply Gauss's divergence theorem to. Pausing again. What do you think? Is everybody okay? The thing we're interested in, not a boundary, but when I play this little minus sign game, I connect it to, it's not the same as, but I connect it to a flux through something that is a boundary, and because it's a boundary, I can wave the magic wand of the divergence theorem. Yeah?
So essentially what we're doing with the integrals is that we're calculating the flux through that unit sphere in the vector field?
Yeah. That's right. So the what we're interested in, let me just get rid of all this. So I'm not drawing the vector field on here because my picture would get all messed up, right? But we've got this vector field. There is some, I don't even know, who knows, it's not really even quite the point what this vector field looks like for the purposes of this example. But if you have some vector field like that, then that vector field through our surface called S, which again, inward oriented, kind of annoying, but yeah, surface and flow, and we can talk about the total flow rate of, how much flow of this fluid per unit time is going through that surface. And you'll notice, like over here on the left side, that's positive because the orientation of the surface is the same direction that my little hypothetical drawing here of the fluid. So I'd get positive over on this side, but I'd get negative over on that side. And so I'm interested, the question is to compute that total flux of that vector field. Yeah. Yes?
Why is it that you do have to negate it?
Yeah, because the orientations are a big deal, right? Orientations matter. And in glasses, in this case, my big picture strategy is to try to compute this with the divergence theorem, but I can't because it's not a boundary.
So you just do it just so that it'll go along with the convention?
It's not a convention, it's a condition. Yeah, so this is a critical fact, right? For the theorem to work, this surface has to be a boundary, but it isn't. But when I play the minus sign game, right, I get the negative if I sort of orient the opposite way. This surface is a boundary, and that's what allows me to use the theorem. Is that cool?
And that's because it's a solid sphere?
It's because it's a boundary. The sphere is a surface. The solid on the inside is called a ball. I know it's a fussy distinction, but we have to. It's an important distinction, and that's how we use the words to kind of separate those out. That's right. So we have a solid ball. The boundary is pointed outwards. The question was about something pointed inwards, and I have to recognize that those are not the same. Yeah.
So is that negative sign just saying that the flux is entering? It's like entering more than getting out?
I missed part of what you said. I'm sorry.
So the minus sign there in the final response
yes.
is saying that the flux is actually getting in and not getting in. Like there is more getting in than getting out.
The minus sign, let's see here. Let's think about, well, okay, this is confusing because let's look at the final answer, right? The flux that we were interested in, the inward flux that we are interested in is negative, right? So inward flux being negative, I mean, inward flux says how much is the fluid sort of flowing inward. The fact that it's negative tells us that the outward flux, had this question been about outward flux, we would have gotten a positive answer, and that means that this fluid is flowing outward. And all things considered, adding up over looking at all directions, etc., it might not be perfectly exactly radially outward, but yeah, right, yeah, okay, yeah.
So this is so the whole purpose of this is to change the surface integral to just a triple integral on a...
I think it's a little overstating to say that's the whole purpose, but that's the punchline that we're capitalizing on here. Yes, is that if I'm interested in a flux, then I have an opportunity to reconceive of it as a triple integral over solid. Yeah, it's just a computational tool, kind of like integration by parts, right, from Calc 1. Integration by parts turns integrals into other integrals that we, fingers crossed, hope will be nicer. And so here I'm turning an integral that would have been really ugly to compute, right? I mean, check out this horrifying nonsense, right? And it's going to turn it into a different integral. And fingers crossed, come on, simple, right? and it's going to work out very nicely, as we'll see in just a moment. Let's go ahead and get to the good punchline. So we have successfully turned this into a triple integral, minus sign, in recognition of the orientation problem. And we got to compute the divergence. So we're going to have to take this vector field. We're going to have to compute the divergence of it. The divergence turns out to be 3 plus x. And even though that's not, like I was kind of hoping for a constant. Honestly, I was hoping for 0, right? That's my favorite integrand, right? But even though it's not the favorite I've ever seen, it's still way better than this nightmare, right? And so huge improvement already. All right, now how do you compute this thing? Well, again, you got to rummage through your toolbox and think about what your options are. It's a triple integral over a ball. There's a pretty strong temptation, since we're talking about this ball, to maybe think spherical coordinates or something, and that wouldn't be unreasonable. That'd be a pretty good instinct. Now, I like to show you all slick examples where stuff works out great when you use the right tool. So I deliberately set this up in such a way that good things would happen, as they sometimes do, when you break this integral up into two separate integrals. Because even though this integrand is not a constant, and it is not odd over any of the available plane options, the left piece is a constant. That turns out into a simple geometry problem. And this right piece is 0 by symmetry, and again, details to think through. Make sure to think through all of the fussy little distinctions that we have to worry about with that. Is that cool? So it's another nice tool for your toolbox. Always be on the lookout for this kind of thing. This happens so much in my physics classes way back when. Oh my gosh, where you have two terms in your integrand and just break it up into separate integrals and you crush them by different methods. Really, really nice. Okay. All right. Now, as it turns out, let's see, going back to our statement of our theorem. Where did I put it? Here it is. Going back to the statement of our theorem, right? Gauss's divergence theorem, being, as this is about surface flux through a surface, which of course lives in 3 dimensions, turning as it does into a triple integral over a domain, of course, in 3 dimensions. This whole theorem happens in 3 dimensions. Oh, we live in 3 dimensions, right? How nice, right? So this is a theorem about the world we live in. And As such, hopefully it's not too surprising that there are some powerful applications and interpretations, and I think this class wouldn't be complete if we didn't talk about, I'm not going to say the most important ones, but the most conveniently accessible ones, and I think the best choices of introductory examples. So I'm going to start with my favorite first physical example, and that is a light bulb, such as we have in this room, right? Light bulbs are fantastic physical manifestations, physical metaphors for Gauss's divergence theorem. This is kind of surprising how this works out. So just to establish the model we're going to be thinking about here, I'm going to imagine a light bulb where there's basically I'm going to kind of think of it as a point source of light. Now, it's not. There's no such thing as a single point source of light. But there's really small sources of light, right? The little LEDs they're making these days are itty-bitty tiny little things. And the bulb itself, to protect it, is larger, and it serves a different purpose. But the actual light source, the LED itself, is a teeny tiny little thing. Okay. And that spits out photons, little particles of light. That's all that is, all you need to know about photons. Little particles that communicate light. And there's a strong flow of photons outward from the bulb. And, of course, it turns into a weaker flow the farther you go out. It's just not as bright out there. And this, by the way, is not in terms of velocity. Remember, we have these two different interpretations of vector fields concerning fluids. Here, the vector field F that's representing this flow of photons is not velocity. Speed of light's a constant, right? Well, that is asterisk. But anyway, basically a constant. In this context, I'm talking about density times velocity. To recognize that there's lots and lots of photons right here next to the bulb that are moving at speed of light, right? Further you go out, there are fewer. They've spread out more. There's less density of photons out there. And so even though the velocity is the same, the density is lower. And so the field, density times velocity, also smaller, as I've got it drawn here. Y'all buy that? Okay. All right. Okay. Well, that said, this setup being arranged, let's talk about the flux through a sphere. I'm going to imagine a sphere like this. Well, there's a lot of flux through that sphere. LED in the middle is spitting out lots of photons. All of the photons that come out of the LED are going to pass through this sphere, and you will have a lot of flux. Right? There's a lot of photons per unit time. There's a lot of it measured on this sphere. Now, where are those photons coming from? Are they coming from the sphere? No, man, they're coming from the LED. Right? That's where the flux, even though you measure the flux on the sphere, that's not where the flux is happening. The flux is coming from the bulb, right? The LED, the thing that's generating the photon. That's where ultimately where the flux that we're measuring out here is actually coming from. And this is perfectly reflected in how divergence would compute. And so in particular, if you look away from the LED itself, everywhere other than where the physical LED is, the divergence is 0. You can write down exactly what the vector field is. Not even that big a deal. We're going to do it in a couple minutes. You can just totally write it down. You can totally compute the divergence, and you will get 0. Indicating, as it should, that, these points over here, that's not where the boundary flux is coming from, right? Why do we have a bunch of flux through this purple boundary surface? It's not because of what's happening here. These points right here are kind of off-center right? These off-center points, photons fly right in and fly right out. That's not a source of photons. The source of photons, where the divergence is large, where the flux is actually coming from is, again, of course, the bulb itself. So that's where the flux is really happening. That's where the photons per unit time are coming from, and divergence specifically is indicated. Okay, how we doing on that? Is that cool? I like this as a first example for the divergence theorem for a couple of reasons. First of all, it's really great for this. Y'all have heard me pitch a bunch this idea of measured on the boundary, but actually coming from the interior, and again, hard to argue with. It's just a very physically incontrovertible. Yeah, of course that's where they're coming from. So I think this is really useful for that conceptual idea, which I think is really important for really deeply understanding what the theorem is doing. It's a fantastic example for that reason. But also, there's the little fact that light bulbs are relatable. Right? I mean, it's an everyday thing, and so being relatable makes this easily digestible. Okay. All right. Okie dokie. Let's look at the next example. Now, my next example is a little bit of a weird one. That's a totally different scenario. There's no photons in this next example. Totally different kind of a fluid. And so, a little strange here, but imagine a fluid that's just flowing radially outward. And in particular, what I like to think of this as is imagine you have a gas, you're out in the middle of far out space, right? And there's some gas cloud out there. And what would happen if somehow or another the temperature started to rise? And I don't know if y'all have had any physics classes, but when you have a temperature, an increasing temperature, then the volume will start to expand, right? So imagine you have a lot of gas, the temperature starts to go up, and all of the gas starts to move outward. Now, of course, gas that starts here is going to be moving outward, away from the center. That's what outward means. Gas that is at the center, if the expansion is radial, as I'm describing, it wouldn't move at all. The center remains the center. Right? And so then you can kind of fill in the blanks in between. The closer you are to the center, the less that gas is actually moving. So I claim that what the vector field would look like as a formula would be that right there. And of course, when you think about it, if the gas is all expanding, then it's still the same total amount of gas. We're not making new gas. Right? Same amount of gas, but it's spread out over a larger volume, and that means that the density is going to be decreasing. Yeah? Anybody see my scenario that I've created? Okay, so with that in mind, wrong button. With that in mind, I want to think about this sphere right here. Again, I want to talk about what's happening on that sphere. And, if you have this outward expanding gas, it's going to be, some of it is going to be passing through this sphere. We have a positive amount of flux. What does that mean? We have this sphere. It had a certain amount of gas inside of it. Outward flux means a bunch of that gas is leaving. We had a certain amount of gas. Now we're having less total gas, right? So the total amount of gas is leaving. Total amount of gas is decreasing inside of the sphere. Is that cool? Okay. All right, and we know that means that the overall density is decreasing. So what interpretation would we make of writing down the divergence theorem here? It's a different interpretation. In this case, by the way, the divergence is easy to compute. You can just plug this vector field in and compute the divergence. Nice little exercise, by the way. Make sure you can do that. I've written this in vector form, but you write this in coordinate form, and you plug into our formula for divergence, and you will get 3K. as a divergence. Make sure you can do that. If you have trouble with it, you're not sure how to start that, talk to me in office hours. Straighten that out. You get 3K. So what is that 3K telling us? Well, the big idea is the whole flux that we detect on the boundary, it represents the overall density, the average density, you might say, decreasing. You could also think of it as that flux measures how fast quantity of gas is leaving, how fast we are losing overall quantity. And divergence, representing as it does flux per unit volume. Okay, let me say it all over again. How fast we're losing gas per unit volume, because that's what divergence is. Well, how fast we're losing quantity of gas per unit volume. Okay, let me rearrange the words. How fast we're losing quantity of gas per unit volume. It's how fast are we losing density of gas. So we get a different physical interpretation in this sort of different physical scenario, but again, pretty natural, I think, and I appeal to your sense of physics. As the gas is expanding outward, as the temperature is increasing, that the density should be decreasing in a uniform way, and that's why the divergence is constant. So again, everything kind of fits together. So I emphasize you have to think carefully about your physical scenario when you're making interpretations of divergence, and in particular, notice that a flow of photons and a flow of gas, these are very different things. For one thing, when you have a light bulb and you're generating photons, you're creating new photons. You're making photons. We're not making gas. Right? So the vector field represents a physically, very fundamentally different kind of a fluid. Right? We're generating photons. We're not generating gas. Also different. The photon density never changes. The number of photons per unit time right here, it's not like we're collecting photons. The photons flow in and flow out. Right? So the density of photons here never changes. The density of gas here totally changes. That's the whole point. Right? So again, physical, what the vector fields represent is totally different physics, and so you get a totally different physical interpretation of divergence. So just make sure to always think carefully about what kind of a fluid you're actually dealing with, how does it behave, and then interpret accordingly. And just a real quick, I'm going to wave my hands at this story right here. There are some kinds of fluids that are kind of a combination that have both of these features, where you're generating fluid, but the fluid density is also changing because of whatever the scenario might be, and that's a much bigger discussion. But ultimately, the point is that these two ideas of creating fluid, of density changing and of actually creating fluid also, you can combine these together in a very convenient way to relate them both to flux. And so, anyway, this can all be dealt with, and that's just beyond what we're going to do in 219. Okay. All right. Okay, let's talk about gravity. Another really important example, sort of, I like to call it a manifestation of the divergence theorem. So real quick, I hope you all remember the formula for the gravitational field. We talked about this back in chapter 3, I guess it was, right? We wrote this down right here. That vector field looks kind of like this, which might look familiar. In fact, it is literally exactly like what you see inside of the orange box here is literally exactly the same picture that I drew here when we were talking about light bulbs generating photons. It's the same picture. It's the same, right? So radial, always outward, and also stronger, closer to the middle, weaker, the farther you go out. It turns out, and this is details that you can worry about if you really want to, but it turns out that the vector field representing the fluid flow of photons coming out of a light bulb is structurally identical to the vector field representing gravitational fields. And that's very non-obvious. It's very, I would say, unexpected, right? Because this is about forces. Gravity's a force. It's not a flow of a fluid, right? Or is it? Now, this is the weird thing. One thing you can do when you're playing around with math ideas and physics and stuff like that, when physical things behave mathematically in a way that's exactly like some other physical thing, you have to entertain the possibility that you might have, in fact, just misunderstood fundamentally what that thing is. So there is a point of view that says we have always misunderstood what gravity is. That gravity is some force that pulls us downward, right? The algebra, the vector field, and how we write it would be exactly the same if gravity were actually communicated by little particles, kind of photon-like little particles that shoot out of, not light bulbs, but that shoot out of mass. Right? And so there's a point of view on this. I don't know if I would be appropriate. My physics is not quite up to this level. But I don't know if it would be quite appropriate to call this a theory. But it sure is a fantastic metaphor. And this is, aside from very, very, very advanced physics that you're not going to ever have to worry about, you can always think of gravity this way. You can think of gravity as being kind of like light bulbs shooting out photons. Except it's not light bulbs, it's mass. Mass shoots out little particles that they call gravitons. I did not make that up. That's a real word. It's kind of cool how the algebra makes that happen. I mean, the whole reason that we think of gravity possibly being communicated by little particles shooting out of mass is because the vector field is exactly what it would be if that's what the underlying physics actually were. It's exactly indicative of that. It doesn't prove anything, but again, you can play make-believe with this and you'll always get right answers, so you might as well. Okay. So with that in mind, that allows us to make some really powerful observations down here. Let's start with this one right here. What does this say? This just says that, well, however much mass you have, look, the amount of mass is shooting out gravitons. More mass, more gravitons. And if you think about it, all the gravitons that get shot out of the mass, all of them have to flow outward through this sphere. Right? So if you're interested in the flux, the gravitational flux through a sphere like this, that gravitational flux is just measuring how many gravitons are flowing through there. How many gravitons are flowing through there? Well, all of them. How many gravitons are being created? Well, it's proportional to the mass. That's the big idea. So this is actually a tremendously deep statement about gravitational flux being proportional to mass. Tremendously deep statement, right? But ultimately, it's just a natural sort of interpretation if you take this graviton point of view of gravitational fields. And by the way, this constant right here is just a detail. That's you've got to work out some algebra to figure out what that appropriate constant is, but it's just a constant. Okay, so we're practically there. Am I out of time? Am I? Yeah, all right, I'm out of time. Okay, so we will pick up here on Monday. Y'all have a great weekend. See you later.
I'm your Professor Bray.
Yeah, thank you.